its application to homological mirror symmetry. And so this is a joint work with Masahiro Futaki. And I've already given a talk last summer in Beijing, and so I try not to repeat the same talk, and well, I would like to change the exposition as much as possible, and also I try not to repeat the same joke as that time. And well, so let me start with an introduction.
I'm sorry.
Yeah?
Can I make just one announcement?
Yeah, sure.
So right after this lecture, there will be some photo session. So before the back.
First, let me fix some notations. So, well, from toric geometry. So let n be a lattice of rank n, and n be the dual lattice. And R is it's an R vector space, and we use the torus. Well, this is a torus which acts on the toric variety, and this is a dual torus. Well, and we also use real tori. T and T check. And let me give a schematic picture of the story. So we start with a convex lattice polytope in NR. A convex lattice polytope. By a convex lattice polytope, I mean the convex hull of a finite subset of n, the lattice n. And from here, well, we associate two, geometric objects. One is a Laurent polynomial. So it's an element of the group ring of n. This is a Laurent polynomial. So which gives a map. So from P dual to C, and the other one, which is mirror to this one, is a toric Fano stack. And the torus T is inside of X as an open dense orbit. And with these two objects, we associate two triangulated categories. Well, one is the Fukaya-Seidel category of W. or the derived category of it. And the other one is a derived category of coherent sheaves on the toric stack X. And that. Sorry?
Is it reflexive polytope or not?
Not necessarily reflexive. So if it's reflexive, then we get just scheme and not stack. But well, it's far more general. So So you have infinitely many examples in each dimension. And here the relation between delta and W is such that, well, W is a general Laurent polynomial whose Newton polytope coincides with delta. So let me write in this way. Well, delta is a convex hull of omega in n such that A omega is non-zero. This is the Newton polytope of W. And well, just one word about the Fukaya-Seidel category. It's an infinity category whose set of object is a distinguished basis. Of vanishing cycles. Well, I will discuss in example, well, shortly, vanishing cycles. And the spaces of morphisms are Lagrangian intersection flare complexes. And so, as an example, let us discuss the case when W is the mirror of P2. One thing I have to say. Well, so the homological mirror symmetry that I'm going to discuss today is an equivalence of triangulated categories or triangulated infinity categories between these two categories. And it is conjectured by Kuntsevich and studied by many people like Oruk, Katarkov, Abu Zaid, and many others. And well, this is it. And yes.
So, for example, if you take feasible surface,
so here's smooth surface.
feasible surface.
Yes.
So F2, then you take the polytope of that.
Yes.
There's a convex lattice polytope.
Well, so no. So we need fun assumption, and if you.
So you have some condition on the lattice polytope.
Sorry, what condition? Well, probably I have to say one more thing. I assume that, well, the origin is in the interior of this polytope. Oh, sorry, I forgot to mention that. But so we need this condition, and so And in the Hilbert surface case, so if you have, well, Fn for n bigger than 3, then, well, then the polytope is not convex. So if you take a convex hull, then you get some toric Fano stack, which is not Hilbert surface. And Hilbert surface, well, the derived category of coherent sheaves on Hilbert surface appears as a semi-orthogonal summand of the derived category of this toric Fano stack. And its relation with, well, and so this gives a weighted projective plane, and the relation between homological mirror symmetry for Hilbert surfaces and weighted project planes is discussed by, well, Orr, Katsarkov, and Orlov's paper. And here, let me discuss a simpler example, which is, well, done by Seidel. So Seidel proved homological mirror symmetry for P2. Well, and so in this case, well, X is P2, and the polytope is just the convex hull of 1, 0, 0, 1, and -1, -1. Well, so this is delta. And in this case, so we have, well, 3 critical values. So the fiber of W is singular if and only if T is 3 zeta or 3 zeta squared, where zeta is a primitive cubic root of unity. Yeah, thank you. And so on the W plane, we have 3 critical values. And we choose the origin as a base point and choose a distinguished set of vanishing paths as straight lines from the origin to the critical values. And then the fiber over the origin is a smooth elliptic curve minus 3 points, which degenerates as you, well, parallel transport along the vanishing path. So it will look like this. And the vanishing cycle is a cycle, well, it has also appeared in previous talk, but so which vanish along the path. And so that's a, well, in this case, the fiber is complex one-dimensional, and the vanishing cycle is an, well, circle on a fiber. And so in this case, so this is a fiber. This is an elliptic curve. Minus 3 points. And we have 3 vanishing cycles, which will look like this. Well, so these 3 points are the points missing from W inverse 0, and these 3 lines are vanishing cycles, which are, well, S1 on this torus. So these are and Seidel have computed that well A infinity structure on these vanishing cycles and shown that it's mirror to the derived category of coherent sheaves on P2. And before going further, let me recall the definition of coamoeba appearing in the title. Well, let R be the argument projection from this torus. So this is where the W is defined, and to the real torus, it's just the argument map. And the coamoeba is just the image of a subvariety of a torus by the argument map. This is the coamoeba of the fiber. And so in this example, the coamoeba looks like this. The picture looks exactly the same as that one, but this is a different picture. So this is the argument x coordinate, and this is argument y coordinate, and the coamoeba is the union of the interiors of 6 triangles and vertices. So this is the coamoeba of W here. So this torus maps into this union of triangles, and vanishing cycles will be mapped to like this. So one vanishing cycle goes here, and others will look like this and like this. And so from here, we get this picture as an schematic description of the behavior of the argument map well, or the behavior of, well, vanishing cycles by the argument map. And let me call this the tropical coamoeba. This terminology have been introduced by us, and if you have any better suggestions, then, well, it's welcomed. And, well, good name is, I think, important for, well, to, yeah. Well, anyway, and, well, this is, well, in dimension 2, it is called dimer models, and the relation between that, well, coamoeba and dimer model is first pointed out by Fenn, Kenaway, and Vafa. And, well, one remark about the naming. Well, so recall that the tropical curves are spines of amoebas. Well, and they, well, appear extensively in, well, Abuzai's work on homological mirror symmetry. So in this case, the amoeba, so amoeba is a map of as a variety of a torus, not by the argument map, but by the map which sends, well, a coordinate to the log of absolute value of that coordinate. And in this case, the amoeba will look like, I think, like this. And and the tropical curve appears as, so this is amoeba. Amoeba is defined by Kapranov, Gelfand, Kapranov, and Zelevinsky, and it's well, sometimes called it spine, but and as a kind of skeleton, we get a tropical curve. And so this is an analog of this relation between amoeba and tropical curves, or tropical hypersurface in general. And so a tropical coamoeba, well, we have a definition, but it's not. Here, just let us give a sketch of what it is. It's a polyhedral decomposition of the real torus into an ordered of polytopes. So well, so pi are polytopes, and well, satisfying, and with some conditions and additional, well, sorry, let me insert of W and additional data, some data coming from flare theory, and so that we have the following correspondence. So so we write a dictionary here. So each polytopes corresponds to vanishing cycles. And it corresponds to the object. And
do I think that that's really the boundary of the polytope?
yes, actually the boundary of the polytope. Yeah. And facets corresponds to intersection of vanishing cycles, and this corresponds to morphisms. And code dimension 2 faces corresponds to holomorphic disks. And which corresponds to compositions in chiasidal category. And so with a tropical coamoeba, one can associate a directed A infinity category and if G is a tropical coamoeba of W, Laurent polynomial W, then, well, these conditions, well, that I mentioned but didn't actually write up, well, these conditions ensure that the Kaya category is, well, let me iron. Well, write this AMPD category AG, and then the Kaya category is equivalent to this AMPD category AG, and one advantage of coamoeba is, well, and tropical coamoebas is, well, that it encodes the information of not only the, well, Kaya category of W, but its pullback to the universal cover of the torus. So let me consider, let W tilde be the pullback of W by, so W is a map from this torus, which is dual to the torus acting on the toric variety, to C, and by the exponential map from, well, let me call this MC, and there's an exponential map from here to here, and so by putting back W by this map, we get a function on MC, and we can talk about the Kaya-sidal category of W tilde. Well, although W tilde have infinitely many critical points, and, well, it doesn't cause any problem, well, and we can define the Kaya-sidal category of W tilde, and let G tilde be the pullback of G by the universal cover of T check by MR. Then we can associate, well, then, well, a directed A infinity category to G tilde, and we have, well, the equivalence between the Kaya category of W tilde and the A infinity category associated with the pullback of G. So this is a tessellation of this, well, vector space. And so for each, well, polytope, we have a, well, vanishing cycle of W tilde. And so then we can, well, using this, well, notion of tropical coamoeba, we can divide a homological mirror conjecture into two steps. Well, and so and we assume that the origin is in the interior of delta, and the first conjecture is the existence of a generic Laurent polynomial whose Newton polytope coincides with delta and a tropical coamoeba of W. And the second conjecture is the relation with the mirror. So the derived category of P equivariant coherent sheaves on X is equivalent to the derived category of the A infinity category associated with the pullback of G to the universal cover of the torus. And so these two conjectures implies the torus equivalent version of the homological mirror symmetry for toric Fano stacks. Which in turn implies homological mirror symmetry for toric orbifolds of X. So let so there's a generic Laurent polynomial with whose Newton polytope coincides with delta, and a tropical coamoeba for this choice of W. So and then the existence of the fact that W is a tropical coamoeba G is a tropical coamoeba of W implies this equivalence. So this is this states that there's a very nice choice of W, so that the flare theory of vanishing cycles of W is encoded in a polyhedral decomposition of the torus. So this is conjecture A.
So G is determined by W.
Well, yes. Well, actually, it should also depend on the choice of a distinguished basis of vanishing cycles. And so, this is a bit loose way to write it, but.
Do you expect for some W, for some very nice?
Yes, yeah, for some very nice W, and for some nice choice of distinguished basis of vanishing cycles, the Fukaya category will be described in purely combinatorial way. So there should be some way to encode all the information into a polyhedral decomposition. And so let phi be an homomorphism of abelian groups, and which is regular, and then we have a homomorphism of the torus, and let K be the kernel of this homomorphism, and let phi star be the transpose of phi. And so we have the transpose map between the dual toric, and then the torus equivariant HMS for X implies, well, then homological mirror symmetry for the orbifold or quotient stack of X by K. So for any choice of K, well, so this is homological mirror symmetry for toric orbifolds. So if you prove these conjectures A and B, and then we, for each, well, solution, we get an infinite sequence of examples where homological mirror symmetry holds. They are, well, toric orbifolds. And the theorem is the following. Oh, sorry, yeah, thank you. Yes. So for example, if you choose K to be a trivial group, then you get the ordinary homological mirror symmetry. And me holds for the projective space for any n. And in this case, G is the decomposition of, well, the real torus into n plus 1 Permutohedra of degree or order n plus 1. Into n plus 1. Order n plus 1. So let me recall the definition of a Permutohedron. Well, so it is a convex hull of the orbit of the point 1, 2 dot n plus 1 by the natural action, the natural permutation action of the symmetric group. So this sits inside a hyperplane in R n plus 1, well, defined by this equation. Well, So it's a polytope inside a codimension 1 hyperplane in Rn plus 1. And let me give an example. Well, the case n equals 2 is too simple, so let me discuss the, well, in this case, n equals, so n equals 1 case is too simple, so let me discuss the n equals 2 case. And so in this case, we have 6 points. So well, for example, one. So let me first we have 1, 2, 3. So the point 1, 2, 3 is here, and then, well, for example, 2, 1, 3, and we have 3, 1, 2, and I think 3, 2, 1, and we also have, well, 2, 3, 1, and we have, well, 1, 3, 2. So this is a Permutohedron of order 3. So this is P3. And in one dimension higher, P4 is a, well, something called truncated octahedron. It's a polytope with 14 faces. And, well, it's also not very difficult to write it down explicitly, but, well, I'm afraid I don't have enough time to write the 3-dimensional picture, well, with, well, 24 vertices. So, well, and that facet of this Pn plus 1 corresponds to division of, well, the set of n plus 1 points into 2. And so, well, actually this corresponds to, well, a hyperplane defined by this equation. So, for example, for example, this, well, edge, this facet corresponds to, well, so this is given by, well, x2 plus x3 equals 3. So in this case, b1 equals 2, 3, b2 equals 1. And, well, or for example, this part corresponds to x3 equals 1. So b1 is 3 and b2 is 1 and 2. And codimension 2 faces, well, maybe I skip it. And the translates of this Permutohedron, the Permutohedron, by the lattice lambda generated by, well, Li n plus 1 ei. Ei are just the coordinate vector minus e1 plus en plus 1, and where I runs from 1 to n plus 1. Actually, I equals n plus 1 can be written as a linear combination of others, but it's no problem. And tesserades H, the hyperplane, and which can be identified with the vector space associated with this lattice lambda. And for example, in this case, L1 is, I think this L1 is, yes, 2 minus 1 minus 1, and L2 is minus 1 2 minus 1, and L3 is minus 1 minus 1 2, and these three vectors, and by translating this this hexagon by this that is we get something like we get tessellation like this, and this will cover the whole plane, and so this works in any dimension. Actually, this is well known in the theory of these polytopes, and let M be a sublattice of index n plus 1 generated by Li plus L1 plus ln, where I equals 1 to n, and then let pi be the translate of the Permutohedron by I minus 1 L1. Then they tessellate the torus. This torus, and we choose W to be of this very standard symmetric form. Then, and then Li, well, we choose a distinguished basis of vanishing cycles. Well, so these are inside the fiber over the origin and coming from the straight lines to the critical values. And let EI be the generator of the derived category of coherent sheaves on the mirror Pn, given by Bailinson. Then, we have a correspondence, nice correspondence between these, three things. So then, the hardest part is to compute the do Fourier theoretic computations in the Sky category. And this can be and this space together with infinity structures can be computed inductively using Seidel's technology. Using symplectic Picard-Lefschetz theory. Developed by Seidel. And so here we have the intersection of Pi and Pj, and this should correspond to the hom of Ei Ej, and which turns out to be given by a vector space like this where V is is an n+1 dimensional vector space. So from here we take and then this corresponds to then the facet of Pi corresponding to this decomposition. So the essential part is the one part in the Fourier theoretic computation which is made possible by inductive method to compute the computations in Sky category developed by Seidel, and then we use argument map to relate it to the combinatorics of Permutohedra, and then this part is well known and classical. And so this, well, gives a very nice description of both these Lagrangian intersection flare theory and then, well, derived category coherent sheaves. And this enables us to prove the torus equivariant version, and hence then, well, the homological mirror symmetry for orbifolds. And well, I stop here. Thank you very much.